Okay, we're asked on this question to decide whether this integral from 1 to infinity of the square root of x to the 7th plus 8 divided by x to the 6 dx, whether it converges or diverges. And so I recommend that we use the limit comparison test, so I call that the LCT, to make this. So we're going to want to find a function that we can know that it either converges or diverges, and then we want to consider the limit of that function divided by our given integrand. And if that limit exists, then we can say the functions, both of them, either both converge or both diverge. So again, in kind of math ease, if f of x and g of x are continuous on the interval, so our interval here is from 1 to infinity, so in general from a to infinity, and if you look at the limit of f of x divided by g of x, and it is some constant, so number between 0 and infinity, if you can show that that's the case, then it turns out that either f of x and g of x either both converge or both diverge. So the idea again is to find a function that you can compute, you can decide whether it converges or diverges, and then do the limit comparison test. If you do get it to be a limit, then you'll know that the other one converges or diverges. So the trick then becomes, what should I let my, f of x and g of x be? All right, so let's go ahead and let the g of x be the original integrand. So that was our square root of x to the 7th plus 8 over x to the 6th. And a good f of x would be just without that plus 8 in there. So that would be the square root of x to the 7th over x to the 6th. And I'll show you why that's a good choice in a minute, because that's going to be one that is going to be easy for us to decide whether it converges or diverges. Okay, so then we will continue here by looking at that limit. So if we look at the limit of f of x over g of x as x goes to infinity, that will be our f of x, which is the square root of x to the 7th over x to the 6th divided by the square root of x to the 7th plus 8 over x to the 6th. All right, so you can simplify that fraction in the bottom, you can flip it. So you're going to have the square root of x to the 7th over x to the 6th times x to the 6th over the square root of x to the 7th plus 8. So our x to the 6's will cancel. And then you can think of this as, you can put that all over 1. So this would be x to the 7th over 1 radical, x to the 7th plus 8. And then the technique here would be to divide everything through by the highest degree term. So if you divide everything through, and we should probably write the limit each time. So this will be the limit as x goes to infinity. So we'll have the square root of x to the 7th. I'm going to divide that by x to the 7th over x to the 7th divided by x to the 7th plus 8 divided by x to the 7th. And that'll be the limit as x goes to infinity. We'll have the square root. X to the 7th divided by x to the 7th is just 1. And then again, x to the 7th divided by x to the 7th is 1. And then this will be plus 8 over x to the 7th, right? And then that simplifies as x goes to infinity. 8 over x to the 7th is going to go to 0. So you're just going to have the square root of 1 over 1, which is just going to be 1. So you do know that the limit exists when you look at the quotient between these two functions. So now all we need to do is consider what happens to our f of x, so the integral of our f of x. So let's think about that. So what is the integral from 1 to infinity of the square root of x to the 7th over x to the 6th dx? Well, you can look at that. I would go ahead and write that it as a single, with a single x. So you can think of this, of course, as x to the 7 halves over x to the 6 dx. And then, x to the 6 is the same as x to the 12 halves. So you have 7 halves minus 12 halves. So that would be x to the negative 5 halves, or would be one way to think of it. or you could think of it as 1 over x to the 5 halves. And then you can go ahead and think of that as the limit to deal with that infinite limit as b goes to infinity of the integral from 1 to b of x to the negative 5 halves dx. And then you can just use the power rule there, so we can think of the limit as b goes to infinity. When you add 1 to negative 5 halves, you'll get negative 3 halves. So this will be negative 2/3 x to the negative 3 halves evaluated from 1 to b. And then if you want to kind of just think about what that's going to look like, we can put the negative 2/3 in front. I'm going to also put this the limit as b goes to infinity. So this is going to be, this is like 1 over x to the 3 halves because of the negative, right? From 1 to b. Maybe that kind of helps. And that negative 2/3, you could even put that in the very front. Negative 2/3, let's think about the limit as b goes to infinity. And this would be 1 over b to the 3 halves minus 1 over 1, or just 1 to the 3 halves. As b goes to infinity, though, this part is going to go to 0. So this is going to be negative 1, and then times the negative 2/3 is going to be positive 2/3. Okay, so we have just shown that that integral converges, and because the quotient of f of x divided by g of x was a limit, because that limit exists, we know that they either both converge or both diverge. So in this case, we can say that they both diverge. So you can just say, therefore, 3 little dots, since that was our f of x converges, and the limit as x goes to infinity of f of x over g of x was equal to 1, we can say that g of x also converges. And, at some point I probably would have thought, we learn about the p series, like in general, this might kind of shorten your work here. If you think about the integral from 1 to infinity of 1 over x to the p dx, you can generalize this to know when it converges or diverges. It's going to converge when p is greater than 1, and then it diverges if p is less than or equal to 1. And so because on that example, we had 1 over x to the 5 halves, x to the negative 5 halves is the same as 1 over x to the positive 5 halves. So the p there is 5 halves, which is greater than 1. So you knew it converged. But you could also, directly show that it converged as we did, through this evaluation of the limit. Okay. All right. Hope that helps.